Hello everyone, I'm Yuan Zhao, and today I'm presenting on behalf of Qiaoyin, who unfortunately can't be here. The work I will introduce is his project, SNARY, a SmartNIC-accelerated Retrieval system designed to tackle the performance bottlenecks of industrial recommendation system. So what's the goal of SNARY? Well, it's to build a high-performance generic retrieval system that can support both exact and fuzzy search. This is really critical for real-world applications like e-commerce and video recommendation. So let's get into it. First, let's set the sense. Industrial recommendation systems follow a two-stage model. The first stage is retrieval, which means selecting thousands of candidates from a huge corpus. The second stage is ranking, where we refine those candidates down to just dozens of items. The retrieval stage is the performance bottleneck. It has to scan millions of items in just milliseconds to ensure a smooth user experience. The goal is straightforward. We want to make the retrieval system faster without sacrificing accuracy, so that the entire recommendation system can respond more quickly. So what is a retrieval system? Most modern retrieval systems use something called embedding-based retrieval, or EBR for short. Here's how it works. First, we load millions of item embeddings from the memory. Second, we calculate the similarity using like dot product between each item and the user's query. And third, we sort all these similarity and pick the top K items as candidate. The challenge here is, how do we do this quickly for large corpora? So what makes an ideal EBR system? There are three things. First, it needs a large, high bandwidth memory to handle accessing the corpus. And second, we need task or data parallelism. That is, we parallelize the access and the calculation process. And third, we need pipeline parallelism, which means we streamline the top K operation with the rest of the processes. SNARY came up with a latency model. It's the memory bound part, which is the corpus size divided by bandwidth plus a constant part, which is based on the pipeline length. The aim is to minimize both of these. So why should SNARY choose FPGA and SmartNICs? Because the CPU is too slow. For the GPU, the top K operation takes up 80% of the latency because of cross-core communication. Then there's the FPGA, which is perfect for EBR system because it has high bandwidth memory, on-chip memory, and it's fully programmable. But why use a SmartNIC? Well, because it's the device closest to user query in a server. Offloading the retrieval task from the CPU or GPU to the SmartNIC can reduce the end-to-end latency. Well, exact search is accurate, but it's slow for large corpora. So in the industry, we often use fuzzy search, which stands for approximate nearest neighbor search, to increase the speed. SNARY choose to fuzzify the corpus access rather than the similarity calculation because it's more efficient. Smaller corpora means the decrease in memory bound part in the formal latency formula. Now, let's look at SNARY's architecture. The high bandwidth memory stores the corpus and the information in fuzzy search. Parallel calculation units compute the similarity, and their throughput is matched to corpus access. There's a filter that balances the throughput between the calculation and top K operation. We have a custom-designed parallel swap top K algorithm, which has a low latency. And we use local sensitive hashing for fuzzy search, which reduces the size of the corpus. SNARY is generic, meaning it can work for any EBR task, and it has high performance thanks to the parallelism of the FPGA. Now let's take a closer look at exact search. First, for corpus access, SNARY uses horizontal storage. That is, it splits the embeddings evenly across different channels to maximize the bandwidth. And second, for similarity calculation, parallel units independently compute the dot product. SNARY turns these units to match the throughput of corpus access. This parallelism minimizes the memory bound latency. Now, the biggest challenge is exact search is the top K selection. The state-of-the-art method in FPGA requires an O of 9K divided by 2 memory, while SNARY parallel swap algorithm only uses O of K memory. And these orders of magnitude memory footprint optimization yield substantial performance improvement, since under a large recall count, the on-chip resources are almost fully occupied, mainly including the memory occupied by the top K module and the filter module. Note that with on-chip memory pressure, the wiring between the memory modules and other logic module will become complicated, which means lead to problems such as wire congestion and tight logic resources, thereby reducing the working frequency. And here's how it works. SNARY maintains an array of size k, and the zeroth position in this array holds the smallest value among the top k values. And for each new score, SNARY compares it with the value in the zeroth position. If the new score is larger, SNARY replaces the value in the zeroth position and then run 2 parallel compare and swap operations to reorder the array, all in one cycle. SNARY also added an early dropout mechanism. That is, SNARY discards scores that are smaller than the current minimum. As a result, the top K operation is no longer a bottleneck. For fuzzy search, SNARY uses local sensitive hashing algorithm in the offline path. SNARY split the corpus into 2 to the power of k's hash buckets. Items with similar embeddings end up in the same bucket. Online, SNARY maps the query to a bucket, and then SNARY accesses the target bucket plus its neighboring. The neighbors are determined by a Hamming distance that's less than or equal to th. This reduces the corpus to a small subset. Then SNARY runs an exact search on this subset. Now, SNARY was implemented on a Xilinx Alvo U50 SmartNIC. This SmartNIC has 8 GB of HBM and 32 channels. The corpus consists of 128 dimension embeddings with 1 byte per dimension. And SNARY turned the batch size according to the value of k based on the resources. And the resource usage under different accelerator card is shown in the table. SNARY was evaluated against FACE, which run on a GPU, and Fairy, which is the state-of-the-art FPGA-based system. Metric used here was query latency, which means latency of a single query, and the latency-bounded throughput, which means the highest throughput, with a latency bounded set to 10 milliseconds, as it's a crucial metric for most recommendation applications. For fuzzy search, SNARY additionally uses a precise metrics like recall, which means the correct ratio in fuzzy search result, and MRR, which means 1/ the most similar element rank. Now for exact search result, SNARY is 79% to 84% faster than face and 21% to 45% faster than theory. For 9 million items and when k equals 4096, SNARY's latency stays below 10 milliseconds, while face can't handle k equals 4096 at all. In terms of throughput, SNARY is 14 to 18 times higher than face and 1 to 2 items higher than theory. And for fuzzy search results compared to face, SNARY is 85% to 87% faster. The throughput of SNARY is 20 to 24 times higher under similarity accuracy. So SNARY is not sacrificing accuracy for speed. We also study the LSH parameters. Is a KH, which represents the hash bit, TH, which is the neighbor distance, and eta, which is the corpus reduction ratio. There's a trade-off here. Low eta leads to decrease in the query latency and an improvement in latency bounded throughput. As eta increases, the search range expands, resulting in improved precision and higher quality retrieval result. User can directly predict the latency reduction and the increase in latency bounded throughput in a fuzzy retrieval based on the parameter combination, allowing for more flexible and efficient retrieval in different approximation contexts. And finally, to sum up, SNARY is the first SmartNIC-accelerated retrieval system that supports both exact and fuzzy search. The parallel swap top K algorithm reduces both memory usage and latency, and the integration of LSH reduces the corpus size while maintaining accuracy. Experimental results show that SNARY significantly outperformed the popular GPU-based solution in both exact and fuzzy scenario, and outperformed the novel FPGA-based solution in exact scenario, which fall short in fuzzy scenarios. Thank you for your attention. If you have any questions, please email Qiaoyin in Slack channel or email to him. Thank you very much.